Fantastic. So before I get going, I want to apologize in advance. The Microbe-Mineral Atlas Center remains very much a work in progress. And the talk I would have given a week ago is very different from this, and the talk I might give a week from now will also be probably very different from this as well, too. So please forgive anything, any shortcomings in today's talk. And I hope that I can advance my slides. Oh. Here we go. So first of all, this work wouldn't be possible without all of these people. And I particularly want to thank my longtime collaborator, Esteban Gatzel, who none of this would be possible without. I also want to thank Chris Mason, Matt Schrank, my co-PIs, along with Esteban in the Microbe-Mineral Atlas Center, and also Joseph Lee and Aliyah Al-Mansouri, two of my graduate students who are here today, who are doing research for their I-Core project on commercializing bioaccelerated carbon mineralization. If they have any questions for you, I'm sure they will. I'd really love it if you could take their questions. So my lab's thesis is that applied biology could revolutionize sustainability. It's already done this in medicine for the past 90 years or so. And we know that biology has this tremendous ability to capture solar power. It captures something like 6 times current world power usage. This is a great proof for the use of biology and technology. So we think that over the next decades, this century, applied biology could help us build a revolutionary new sustainable energy infrastructure. But to build this infrastructure, we'll need new technologies. And I want to stress, especially to the last question, this is an amazing opportunity for creation. There's loads to play for here. There's loads of uncertainty. But that means we can think big. For many of these new technologies, I think we don't just need more engineering. We need more fundamental science. But we haven't got forever. So we'll have to focus our energies on answering scientific questions that can lead directly to new and useful technologies. So how do we do this? So we think that biology offers an enormous range of capabilities for sustainability. And on the left, Jose Avalos, a longtime friend at Princeton, and I drew up what we think of biology in the abstract. I guess this is what happens when a physicist tries to think about biology. We have room temperature and room pressure catalysis, self-assembly, all the way down to the ability to hyper-selectively accumulate metals. And we could use these in all sorts of sustainable energy applications, from enabling the safe use of nuclear power to biomining metals for the sustainable energy transition and other advanced technologies. But I want to stress, we understand very little about biology, even after decades of investments in fundamental science. We don't know nearly enough about the genetics of weird organisms found in unusual places that do the most interesting things for sustainability. And we're trying to figure that out. So do we need a new way to do scientific research? I'd like you to think about this just for a moment and just, I'd say, think about this. Entertain this thought. So whenever we talk about technology today, we use words like unprecedented or remarkable. And certainly in the mid-20th century, it was. Economic growth boomed and hours worked dropped, just as John Maynard Keynes predicted in the 30s. But actually, if you look at the growth of the economy as a whole, especially in the advanced Western economies, or the growth of frontier technology, this has actually been much less impressive over the last 5 decades. And I would argue that, and again, here I'd love you to entertain me just for a second, at least some of our social, cultural, and geostrategic problems faced by the US and other advanced nations might be due to our lack of progress in new real-world physical technologies. Climate change is certainly one of those problems. The critical elements challenge is another one. So is it just a pipe dream, given that headwind, to use biology to build a new sustainable energy infrastructure? And I don't think it is a pipe dream. Little more than 100 years ago, the thought of a worldwide telecommunications infrastructure was a pipe dream too. We only had our first transcontinental telephone call little over 100 years ago. But today, I'm able to speak simultaneously across the planet thanks to the internet. Most of the innovations needed to make this happen were down to one organization, Bell Labs, that harnessed the new science of quantum mechanics to build new communications technologies like the transistor and optical fibers. I think some of our challenges in building new technologies come down to the way we organize modern scientific research. Ever since the Endless Frontier report of 1945, we've thought of research in a one-dimensional way. We've got basic research, so think nuclear physics, and this, at least in this model, feeds directly, a seed corn, as Vannevar Bush put it, into applied research. So things nuclear power, jet engines, radar. But this model might have a blind spot. And I want you to entertain this thought. 30 years ago, 50 years after the publication of the Endless Frontier report, Don Stokes, a professor of public policy at Princeton, he raised this issue. Where are all the new technologies? Where's the productivity growth? And he posited that we should think about research in two dimensions rather than one. The quest for fundamental understanding and the consideration of use. And here we can divide science and engineering into four quadrants. I guess you can't divide it in any other way. We've got the Bohr quadrant, where we have pure curiosity-driven research containing things like quantum mechanics, and applied research, the Edison quadrant, with things like light bulbs, nuclear power. And there's a handful of technologies, a small number that can directly make this crossover, nuclear power and CRISPR. But there's a third quadrant, the Pasteur quadrant, and this connects the two. And here we have the seeds of some of the most useful inventions of the past couple of hundred years. Microbiology and pasteurization, solid-state physics and transistors, aviation and aerodynamics, more recently mRNA vaccines, and I think biomining. And this quadrant allows us to connect pure research that we've done very well over the past few decades to application, which we can also do very well. And we need to reinvigorate this quadrant. And the Microbe-Mineral Atlas Center attempts to do exactly this. One of our biggest problems are metals, and we know, thanks to Liz's talk, that the demand for metals is going to skyrocket in this century. And we think that biology could be an incredibly useful solution to this problem. We know that biomining already supplies something like 20%, between 12 and 20% of the world's copper and 5% of its gold. But there are no commercialized bioprocesses yet for any of the other metals, and we think there are about 40 other critical elements. What this means is we'll probably have to build these organisms through synthetic biology, but we know very little about the genetics behind the most interesting capabilities offered by the weirdest microbes. So my lab's job is to figure this out. And we've already done this with rare earth element biomining as well. So we've been able to dramatically improve rare earth element extraction, increasing it by 1,200%, increase rare earth biosorption by over 200%, and we can even increase the selectivity of rare earth element selectivity for adjacent heavy rare earths, one of the hardest problems in chemistry. And we predict this might lead to an almost 50% reduction in the length of a separation process. Likewise, we've been developing advanced new genetic screens that allow us to go after extraction and separation metals that don't depend upon acids, using direct metal release assays. And I'll talk more about these later. And we can even manipulate these mechanisms. We don't know exactly what they do yet. But we know that if we engineer using them, we can enhance bioleaching further as well. But this is just the lanthanides. These are about 14 of the 40 critical elements. They're all very chemically similar, as Liz pointed out. What about all the other metals and the minerals? And again, here's some of them. The lanthanides are in red, and the rare earths are in red. The others are in blue. And they're hosted in completely different mineral systems as well. We have to remember they're not just different metals, they're hosted in different minerals as well. The first challenge is, even if we build this sustainable energy infrastructure, we know that the need for carbon removal is only going to grow. Even if we stop emitting today, the world will continue to warm. So we need ultra-cheap ways to remove carbon from the atmosphere. Metals are part of this challenge as well. So in nature today, weathering of olivine, one of the most abundant minerals in the solar system, and reaction with CO2 locks up CO2 as another rock, as magnesite. And this could sequester potentially up to 100,000 times the excess CO2 in the atmosphere. But it'll take tens of thousands of years to do it. And we know this from the experience of the Paleocene-Eocene thermal maximum. But we need to do it in less than 100 years. So how do we accelerate this? And we've shown that we can do this with biology. So Joseph, who's here today, and Luke Plant demonstrated that Gluconobacter oxidans, the microbe that we originally biomined to create rare earth biomining technology that we commercialized through REEgen, it also happens that it's the best choice for dissolving ultramafic silicates as well. It leaches by far the most magnesium over other well-known mineral-dissolving microbes, including Penicillium simplicissimum and Sphingomonas desicabilis. And you'll see this difference is enormous. On top of this, Joe was able to show that Gluconobacter, our biggest fear about taking biology out into the real world and commercializing it, is that it'll work well in the lab, but it will work terribly under industrial conditions. But it just happens that Gluconobacter just gets better and better and better under industrially relevant conditions. As we increase the pulp density, the ratio of rock to water, the advantage of Gluconobacter over acids alone increases and increases. And what this suggests to us is it's doing something really interesting with minerals, beyond simply producing organic acids. Something weird's going on here. On top of this, Gluconobacter just gets better and better. It can use highly abundant cellulosic sugars in addition to glucose. So the cost of operation potentially won't break the bank. But can we improve even further as well? So my students, including Joe, have been able to build these high-throughput mineral dissolution screens that directly measure metal release rather than relying upon easy proxies like acid release, that you just use dyes. Joe was able to comprehensively screen the genome of Gluconobacter oxidans. We built a whole genome knockout collection of Gluconobacter using our Knockout Sudoku technology that dramatically reduces the costs of building knockout collections from millions of dollars down to tens of thousands of dollars. And you can see some of the results in panel A on this slide. You'll notice unfortunately I've had to obscure these results as we're still in the patent filing process. What we find, though, is these completely differ from our results for bioleaching monazite, a rare earth-containing mineral. And what this suggests is that microbes use a totally different suite of genes depending upon the mineral they're interacting with. Finally, Leo was able to use this information to engineer Gluconobacter to improve it even further. And the most exciting part of this is, if we'd have just gone from database information, from the results of screening other minerals, we would never have guessed this. We find that a new gene, previously undiscovered, previously completely unassociated with mineral dissolution, almost doubles our previous best commercialized mutant. And Joe and Aaliyah are trying to turn this technology into another company called Gigatonne Bio. That's magnesium. So we've had the lanthanides, we've had magnesium, about 15 elements. We've still got about 25 more critical elements we want to biomine. What are we going to do? We think that microbes use a suite of mechanisms to interact with metals and minerals. The simplest is acid production and redox changes. Acidothiobacillus ferrooxidans, the copper biomining microbe, most famously uses this. They also secrete chelators. Siderophores are the most famous example of this, but so is lanmodulin, the selective lanthanide chelator. Hyperaccumulators, biosorption, and the ability to precipitate metals, which could potentially give them new high-value uses, for instance, in catalysis or advanced materials. But what genes encode these? I also want to ask you to perform an act of imagination as well. Liz pointed out that we now know that biology is able to interact with lanthanides. Now, if you were to go back in time, 15 or 20 years, when I first took biochemistry classes, I would have said, the textbooks would have said, certainly human physiology interacts only with a handful of metals. I could probably count them on my fingers. Everything else was simply toxic to physiology. But there were signs even then that biology interacted with a greater suite of metals. 15 years ago, if you were to say biology interacts specifically with lanthanides, though, you would have been greeted with great skepticism. But the discovery of the XOXF-type methanol dehydrogenases and lanmodulin, which prefer lanthanides by at least a factor of 100 over calcium, indicates something special is going on. What I would ask you to do is imagine that biology might interact with many, many more metals than we currently know. Many of the technology-critical metals and semiconductors, gallium, germanium, antimony, rhodium, you name it. There might be something out there that wants it and knows how to use it that we might be able to exploit for biommining. So figuring this out is going to take a team, the Microbe-Mineral Atlas Center. And I particularly want to call out Esteban, Chris Mason, Matt Schrenk, and our international collaborators, as yet unfunded, but we hope to get them on board in the future, including Louise Horsfall at the University of Edinburgh, Takeshi Kakagawa at Tohoku University, and Yohei Suzuki at the University of Tokyo. So over the past 18 months or so, since we started the Microbe-Mineral Atlas, we've visited mines across America, each of which with different geology, different metals, including the Empire State Mine in upstate New York, the Mountain Pass Mine, and then the Continental Mine, where most of America's copper came from. Here's our first trip to the Empire State Mine in upstate New York. And here are later trips out to the western US in last fall. Since then, what we've been able to demonstrate is there's an enormous untapped reservoir of previously uncharacterized biology. We see this with initial short-read sequencing. Many of the phyla are unclassified. Many of the classes of microorganism are likewise unclassified. Out of the genes that we can identify, we see that there are a lot that are associated with biomining, which suggests that a lot of the genes of unknown function may also be associated with biomining or could be exploited for biomining in ways we don't yet fully appreciate. Likewise, long-read sequencing further confirms this. There are loads of unknowns here. And our sequencing is getting good enough that we're able to identify novel biosynthetic gene clusters as well. We even see totally novel species as well at these sites. They contain some of the core biomining machinery, but they're from genuses that previously have never been associated with biomining, likewise suggesting we may see totally novel capability. But how are we going to exploit this? Many of the microbes probably aren't even culturable, let alone genetically engineerable. And this means we're going to have to lean heavily upon engineering new capability into chassis organisms that we know how to deal with. Gluconobacter is one, and the ultra-fast-growing microbe Vibrio nitrogens is another. But how do we know what genes to add? Sequencing can only take us so far. Sequencing only allows us to tread well-trodden ground. It doesn't allow us to venture into new ground. So we need functional screening. So now, postdocs in my lab, Adam Francisco and Shreya Singh, are working on developing a functional metagenomic screening pipeline where we take environmental DNA from these microbes and then we put it into our chassis organisms and we screen for gains of function. Right now, this week, I think they're going to show that we can rediscover the land modulin gene in an environmental DNA library. But comprehensive screening of enormous libraries, of enormous metagenomic libraries, is likely to require millions of assays. So we're going to have to get really, really good at this. But we're fortunate that Vibrio nitrogens, a microbe that we further developed in my lab, might allow us to do this. A few years ago, David Specht, then a postdoc in my lab, asked this question: why haven't we been able to fully take advantage of artificial intelligence in biology? And he realized that our ability to get DNA into microbes has not substantially improved since the 1980s. He was able to engineer V nitrogens with the TFOX master natural competence regulator that allows it to uptake DNA through a molecular mechanism rather than a chemical mechanism. And this dramatically reduces the capital costs of building ultra-large knock-in libraries. David, along with Cameron Kitzinger and Bryce Brownfield from my lab, started Forage Evolution to further commercialize this. And they're partnering with us on the Microbe-Mineral Atlas and Air Force Research Lab work with Biolithica, another company that's coming out of my lab. So I want to summarize before I run out your patience. Biology might hold enormous potential for mining all sorts of elements that we need for advanced sustainability, computing, and defense technologies. But we can't unlock this with sequencing alone. We need functional experiments to do it. And I hope next time I speak with you, I see some of you, I might have a lot to tell you about this. We think we're on the cusp of making it happen. So thank you for your time, and I'd be happy to take any questions you might have.
We have time for a question or two?
Yes, over there.
Hi, great talk. And I have a general question as to what, in your experience, are you seeing the difference in this extraction using microbes when you compare with, let's say, idealized feedstock as opposed to the real feedstocks in terms of the competitive binding? And where I come from, my question is super specificity always required? Because in real feedstocks, you might not necessarily see the competing elements show up all the time.
Oh my gosh, let me think about that for a second. So if you think my feeling, let's say we talk. Maybe we could. How to break this up into the most. I want to give you a good answer to this question. The short is I don't know. Our first job, right? I talk about sort of this I think there's a sort of we want to operate sort of at this intersection of basic and applied science, right? That still requires fundamental science, and so initially that requires that we work with very, very clean feedstocks, because any complex feedstock can be broken down into sort of a selection of pure model feedstocks. We can understand those alone. That gives us a basis for understanding the complex feedstocks. I think you're right. The initial, I view biomining as at least 3 steps. Extraction, and there you can have you can extract everything, right? That doesn't need to be selective. It does need to be good. It doesn't need to be hindered by the feedstock. But it doesn't need to be selective, I don't think. Then there's separation. And that does need high selectivity. And it also needs to operate in very dilute environments. And ideally, whatever you use to separate, it might be a biosorption, it might be biosorption on a membrane, the technology that we've been pursuing with V-nitrogen's biosorption. Or it could be chelation-based approaches, for instance, that Alta uses with Lanmodulin. You want that molecule, or that set of molecules, to tolerate the leachate conditions. So they do need to be a little bit tailored for it. And then finally, you have this potential to make new materials as well. Liz brought this up with making gold nanoparticles in leaves. Louise Horsfall at Edinburgh has pioneered this technology with platinum palladium nanoparticles. There you can operate that in a pretty clean environment. Again, there's the potential for selectivity as well. I'd be really happy to unpack this with you as well later on too.
Okay, in order to keep us on time, I think I'm going to thank Buz
Thank you
for a
very
great
much.
talk.
And I saw it.
And
Nice.
turn it over to Joel.
And I saw a question over there. I'd be happy to get to you as well later.
Thanks again. And Buz is going to be here for the duration, so there should be a chance for other connections and answering some questions.